Okay, this class is about algorithms and data. It's intended to be a first class in computer science, just like you get in college. And today we're going to talk about algorithms. You're going to learn how to program in in this class. And I hope at the heart that you understand that it's a class about problem solving. And the thing to remember is that computers are not smart. You will in fact hear me say a lot of times, computers are stupid. A computer will keep doing whatever you tell it to do, no matter how smart or dumb that is. But computers have perfect memory as long as you tell them to remember the right stuff, and they can perform tasks really, really fast. So the key is you're going to break up big problems into small problems and keep breaking it up into smaller problems until you've broken it up into problems that are so simple a computer can do it. But because computers are fast, you can solve problems that would be hard for a person to solve. So an algorithm is a set of rules or procedures to accomplish a specific task. You use algorithms every day, even if you aren't aware of it. Let's consider tying your shoes. You should take a minute here to write down the steps to tie your shoes. Pause the video for a minute, tie your shoes, and write down those steps. And I'll give you a few seconds here. Okay, so probably most of you have done one of two things. Either you made the two loops, or bunny ears if you're a younger kid, make two loops and you just cross those over one under the other and pull it tight, and your shoe is tied. Some of you probably made one loop and then wrapped the other lace around that loop, and then pulled through the the opening in the one that you wrapped around, and you got your two pieces that way. Those are the two basic algorithms. Now there's more steps, but you guys both know what I'm talking about. We do this. To get a computer to do it, you'd have to say like, okay, form a loop with on one side pinching the two pieces together so the loop's a couple inches long, and then do the same thing on the other side. Then cross those two over and pull one of them underneath the other. So pull it through that opening you created, then pull it tight is an example of an algorithm. But there are two different algorithms to accomplish the same task. Which is the right one? Well, do they both work? Yeah, they both tie shoes. Is one better? Why do we have two different algorithms if they both work? Think about this. Why did we start with bunny ears for younger kids? We start with bunny ears because they can understand it. It's simpler algorithm. It takes less fine dexterity, so it's easier for little kids to tie their shoes that way. Why do we go away from that? Well, if you tie that way, the knot's a little bit less tight. So the shoe isn't quite as secure. It's more likely to come undone. So as you get older and you have a little more dexterity, you can tie it a different way. A lot of people move to that way. But there's not one that's intrinsically better than the other. They both serve a purpose. And this happens a lot in real world situations, that there are different algorithms to solve something. And sometimes an algorithm will be clearly better, just it's always faster, it's always more efficient. But a lot of times the question of what's the right algorithm depends on exactly what you're going to do with that algorithm, how it's going to be used. So there's a key thing of you need to understand how to evaluate algorithms and how to pick an appropriate one, but don't get hung up on finding the right one. If you find one that works, very often that one is going to be a good choice. So let's try another algorithm here. I want you to write down the steps for you to go from your house to Kaufman. So for me, it would be I start off on Wilson Avenue on the east side of Columbus, go south a very short distance to Bryden Road, turn right on Bryden Road. So I'm heading west on Bryden, it'll turn into Town Street. After it turns into Town Street, I come to Grant. I turn left, which is south on Grant Street. Go south on Grant to Rich. Then I go west on Rich, which is a right turn, till I get to 3rd Avenue. Then I turn left on 3rd Avenue and go south on 3rd until I get to the I-70 on-ramp. Take a right turn to get on that on-ramp. Get on 70 West, and I take 70 West out to the west side of Columbus to the 270 interchange, get on 270 north, and I take 270 north to the 16133 exit. I get off that exit, go to the first traffic light at Post Road, and I turn left onto Post Road. And from Post Road, go to um, Emerald Parkway. That traffic light, I turn right on Emerald Parkway. Now here, if you're an IB computer science, it should say, how do you get to Emerald campus instead of Kaufman? Um, so I'll come to the intersection of Kaufman Road and Emerald Parkway, and I'll either turn right, which stays on Emerald Parkway, and go to Emerald campus, or I go straight, which becomes Kaufman Road, and I get to Kaufman that way. So I have an algorithm. You guys all have an algorithm. All these algorithms get you to Kaufman, or they get you to Emerald campus, but everybody's algorithm is unique, or at least relatively unique. None of you can use my algorithm and get to school because you're not starting in the same place. So it's a slightly different problem, even though the end steps are the same. But some of you, your algorithm will finish the same way as mine, and some of them they're different completely. Ours never intersect. Some of you will have classmates whose algorithms are different than yours up to a point, and then you're both on Emerald Parkway, you're both on Kaufman Road, or you're both on Brand Road, or you're both on Dublin Road, heading the same direction, and then the algorithms are the same from that point. And sometimes you'll get to the same point, but you'll make different choices on how you get to where you're going. And with this traffic algorithm, there are different algorithms. I could choose a different algorithm that brings me up 71 north, or one that brings me up 315 north, or even one where I go east to get on 270 and then come all the way around. And depending on traffic, I might choose a different algorithm. So the key is thinking about breaking that thing down into those steps, right? If you're at my house and I just tell someone how to get from my house to Kaufman, they say, go to Kaufman, that doesn't work. And if I just tell somebody who doesn't know it, I can't say get out to 70 on the west side and then come up 270 to 16133. So you want to be detailed. Just think it's got to be steps so simple even a computer can do it. But you have to evaluate and know that there are different algorithms that'll solve any given problem and figure out and find a good algorithm for the purpose that you have for that problem. So let's think about this in terms of what we just talked about. The initial conditions, the data you start with, dictate differences. And that means, like, where do you start at home? Sometimes algorithms share common steps. A really cool thing in computer science is that a lot of these common steps can be reused, right? You may have a lot of algorithms that rely on determining whether a number is prime or not. But once you've figured out an algorithm for determining whether a number is prime, you can reuse that algorithm in a lot of different larger algorithms without having to reinvent it every time. And that's a really powerful thing. Remember that computer programmers inherently are lazy. And